Hello, this is Ming. In this section, we will walk through the Convolutional Neural Network notebook. Same as before, let's come to the course homepage and then go to the notebook section and copy the address for this Convolutional Neural Network notebook. After the link address has been copied, let's go to the DataBrick Community Edition here. And same as before, we click on the Home icon on the left. In this workspace, on this kind of white space here, we right click and there is a import button here. Click on the import URL and paste the address that we just copied from the course homepage. Then click import. Now, this convolutional neural network notebook is already imported in your DataBrick environment. So basically, it is your notebook. You can modify it, you can write. So again, we need to attach a running computing environment to this notebook, and by this top left part here, click. My test01 is still up and running, so I click on that. So that's basically give us the notebook's running environment. So it's going to take a little while to run. Let's click on the Run All button and wait for the notebook to install the needed library and run through the beginning to the end. So as we mentioned earlier, for images, pictures, the relationship, the spatial relationship among pixels, definitely this is going to help to make us to make the right decision. So on the first example, the feed-forward neural network one, we discard all those spatial correlations we see in the image. We convert a 2D matrix into a one-dimensional vector, and we treat each column to be independently contribute to the model. So a much better solution is using the convolutional neural network, which basically is going to naturally consider the pixel-to-pixel spatial relationship. So the first few steps are exactly the same. We're going to download the Keras library. We're going to install the Keras library for the backend setup. We load the MNIST dataset, the same dataset we used before. And in this particular one, in this, we can also plot a sample image, same as before. Now, for convolutional neural network, is actually going to expect to see a two-dimensional matrix or three-dimensional for videos, or actually for colored picture, we are going to have RGB, red, blue, green, those three different kind of channels. For grayscale, we only have one channel. So for a colored image, the model is going to expect to see a three-dimensional tensor for each image. So the X and Y is going to be the pixel, the Z direction, 3 dimensions, the pixel value for white, blue, and green. So we are going to define a few of those parameters we're going to use for future batch size, number of classes, epochs, the image row, image columns. In this particular case, is 28 by 28. So for the data pre-processing stage, as I mentioned earlier, the convolutional neural network model is going to expect to see channels for colored image. And because we're in grayscale, we have to convert the original data using the reshape function again to be for each image, we are going to have the row, column, and number of channels. It is actually 1 in this particular grayscale example, but we have to have the reshape function to indicate for each data is going to be a tensor. So we look at it, the training data, the X, the features. For each observation, it's going to be 28 by 28 by 1 tensor. We're going to do the scale as well, same as before. We convert the Y, the response variable, into categorical by using the to_ categorical function. Once the model has been, once the data, the input data has been pre-processed, now we're ready to feed a convolutional neural network model. Same as before, we're going to have the curious underscore model underscore sequence function to create a placeholder. Here I call them a CN underscore model. So the first layer, now the layer become a layer underscore CONV underscore 2D, and a two-dimensional convolutional layer. Number of filters, what is the kernels for each filter, the size of the kernels, what is the activation function, what is the input shape. The input shape is only needed for the first layer. And after the convolutional 2D layer, we actually added a max pooling layer. The max pooling layer, as we mentioned earlier, is going to give us the pool size is 2 by 2. So in those 2 by 2, 4 pixels is going to return the maximum of those 2 by 2 pixels. Basically, the max pooling is going to reduce the size of the dimension of the 2D image after applying the max pooling function. Then the second layer, we have 64 kernels. Filters, the kernel size is 3 by 3 again. The activation function is ReLU. We add another max pooling layer. And for the second layer, we also added a dropout layer with the dropout rate to be 25%. So this is basically 2 convolutional neural network layers. After those 2 layers, we're going to have a flattened layer. The flattened layer is basically to convert those 3-dimensional tensors into one very long vector. After we convert this into a very long vector, we'll go back to our original feed-forward neural network. That is, we add another dense layer with 128 fully connected neurons with activation function ReLU with the dropout. The last layer is actually connect all the neurons to the output, the 10 different kind of classes using max activation function. So basically, that is a convolutional neural network which has 2 convolutional 2D layers, as well as flattened layer and 1 fully connected layer, and last connected to the output. It is a relatively small network, but it's basically show the overall structure for some typical convolutional neural network models. We look at the summary of the model. There are a lot of parameters, not surprising, a lot of parameters in this model. After the model structure has been established, we need to compile the model with specific definition for what is the loss function, what is the optimizer, and what is the metrics to track during the model feeding stage, same as before. Now we can train the model using the feed function by indicating what is the training data, what the batch size, what the epochs, and what is the validation split. It's going to take a little while for convolutional neural network. It's actually took 3 minutes. 3 times slower than the feed-forward neural network. That's actually typical because there's a lot of tensor operations. So that is also why the GPUs and TPUs are much better choice for convolutional neural network than CPU. As we can see, the accuracy is actually better than the feed-forward neural network model we see before. So this again, the losses and accuracy as a function of epochs. After the model has been fitted, we can evaluate the performance on the testing data. It is actually 1% higher than feed-forward neural network. Is very good, 99% already in the testing data. We can look at the model prediction, which class for each observation, and we also know the ground truth. By comparing the predicted class and the ground truth, we can check a few misclassified images. Same as before, and this is actually one of the wrongly classified image that could be 9, 0, or 4, possibly for those digits, and image actually for 8, but wrongly predicted as 9. Yes, there could be 8 and 9, 4, 0, all possibilities, but the intention for the writer for this image is actually intended for digit 8, but for this model, it's wrongly predicted as 9. All right, that's pretty much the end for this convolutional neural network notebook.